So hello everybody, you are here for the fine details behind C++ containers and algorithms. The recording is being done again due to technical difficulties in the original recording, only for the first minutes. So after the first minutes, you would get the original recording. My name is Amir Kirsh. I'm a lecturer at the Academic College of Tel-Aviv-Yafo and at Tel-Aviv University. I teach mainly C++, but also other practical engineering software programming courses. I'm also the dev advocate at Incredibuild and the co-organizer of Core C++ meetup and conference. A slide regarding Incredibuild. We do build acceleration. So if you are suffering from slow builds, it is not just waste of time. It affects your dev cycles and productivity. We do build acceleration by distributing your builds to idle machines or to the cloud. Feel free to contact us for details. We also accelerate Yocto builds. You can follow links on this slide and look for details on the web. So again, feel free to contact us on any CI, pipeline, slow issues that you have. We would be happy to assist. The topics for this talk are selecting the right container and using it properly. We would also discuss additions in C++ 17 and 20 and also a bit of C++ 23, using algorithms smartly and a few slides on iterators. So let's start. I think that we would start with vector. So a question to you, what is the complexity of pushback to a vector? We want to add an item to the end of the vector calling pushback. And some of you also already know the answer. The call to pushback, the complexity of calling pushback is amortized O1. So it is constant amortized. And the question is, what does it mean, amortized O1? And how can we know that it is amortized O1? So let's begin with the question of how can we know that it is amortized O1? And the answer is that we know that because the specification requires us to have amortized O1 for vector pushback. When I say requires us, it means requires the library implementer. So the library must have amortized O1 complexity for pushback call. And let's see, what does it mean, amortized O1? So usually we think of vector as a very cheap, very efficient container, which it is, which we all prefer using vector usually. But pushback, when you call pushback, it might be that we are beyond our capacity, in which case we need to enlarge, to resize the size of the vector. And by resizing, we have a new allocation and we need to copy the old elements, the elements from the old allocation to the new allocation. And if we have n elements in the old allocation, we copy n elements to the new allocation, which means a linear complexity, O of n, On. Now, so how can we come to O1? So amortized complexity means that we take a look not on a single call to pushback, not on a single call to the thing that we are measuring or having the complexity calculation. So we want to see what is the complexity of n calls to pushback. And when we do the math for n calls of pushback, we see that n calls would cost On, so amortized single call would be constant. An important side note regarding vector resizing. There are three options when we call pushback and there is a need for resize, or when we call resize. First, if the items are trivially copyable, then the vector just use memcopy or stud copy, or in any case, copies the memory, not the elements, which is the elements, but without regarding each element separately. So copying as a block of memory. On the other hand, if the elements are not trivially copyable, then there is a need to copy them separately one by one, in which case we can either move them or we can copy them. Moving them might be problematic in case the move constructor of the elements might throw an exception, because then we might try to move elements and we may succeed to move some of them, and then an exception might be thrown moving the X element, And then we cannot move back those that were moved already because they also may throw an exception. So we end up with some of the items in the new allocation and some in the old allocation, and we are not in a stable state. So even if we come back to the user saying, okay, you got an exception, he would not get the vector, not with the old allocation and not with the new allocation, because the elements are partially here and partially there. So in case the move constructor may throw, the vector must use copy constructor. So this is the third option, which in a way emphasizes the need to put noexcept on our move constructor. So let's take a look at a short benchmark. This benchmark shows two calls, one with forgetting noexcept, the other one with noexcept. I created a myString class there. It might be a bit small, the font there, but you can believe me that there is a myString class and the same implementation in both cases, but the one is without noexcept. You can see here there is no noexcept, and the other one does have noexcept, and this is the only difference between the two. And you can see here that the difference is costly. You just forgot a noexcept on your move constructor. Don't do that. You would pay for that. So let's go back to our slides. So we spoke a bit about vector resizing. This is the result that we just saw. A side note about stud copy. In some cases, we try to implement it ourselves, but no need to. The language implemented it as an algorithm. If you want to copy items from one container to the other, you can use stud copy. And stud copy, the specification doesn't say so, but again, most implementations would, most probably. For trivially copyable and contiguous elements, they use mem_move, and otherwise would copy in a loop. They cannot move because it is stud copy. And again, if you go to the specification, it doesn't say that it expects the implementation to use mem_move, but the implementation can do that if it wants to give you some performance. There is a very good talk by Roy Barkan from C++C. This is the link to the abstract. The videos didn't come out yet, but you would be able to look for the video later on aliasing or overlapping. When you call stud copy and you have an overlap between the location where you copy from and the destination, there are some functions that deal well with overlapping, and there are others which do not. And again, the specification says when you can use it with overlapping and when not. So this is another talk. So the specification do mention the complexity requirements for many operations on containers, on algorithms. These are a few examples. So you can read it actually in the spec. Let's just, press on one of them. So this is the spec, and you can see that at a certain point, you would see the word complexity. So these are the requirements per many things in the on operations on the container. It is a bit more complicated to read than CPP reference, which is also a bit complicated to read occasionally. But if you look for the word complexity, at some point you may find it, maybe at the end of the table. So you would see that there is some requirement for complexity on something. And the specification says that in order for the implementers to be able to take it as a requirement, and for us users to know what to expect. If you want, you can read it in CPP reference, again, for the same operations. And usually this is something that we want to know. We want to know, oh, what would be the worst case? What is the average complexity, etc. So again, we are after lunch, and this is a question to you. What is the complexity of sorting a vector? What is the complexity of sorting a list? As written in the specification, what is your guess? Go for it.
It's n log n.
Yeah, it sounds like something that should be O n log n. And indeed, this is the case based on something which is like quicksort or quicksort exactly. By the way, for some reason in the past, the specification said approximately n log n. I think on list it still says approximately n log n, and at some point it changed from stud sort used to say approximately n log n, and it changed to O n log n. The reason is that there are some algorithms that are near n log n, and specification wanted to have the ability for the implementer to use other algorithms, but eventually they decided, well, there isn't any real reason for using algorithm for sorting which is not n log n. So a question, if both are n log n for list and for vector, so we need to sort a list, we need to sort a vector. Is there any way, a better way maybe for sorting a list other than calling list sort? I mean, we have a list, we want to sort it. List has a function, sort. By the way, you cannot use stud sort on a list because it expects a random access iterator. That's a very good knowledge of the material. It expects a random access iterator, stud sort. So vector is okay for that, and list is not. Any idea how can we sort a list if not calling list sort? Well, I tell you, or I would tell you what can be an approach. We can copy the list to a vector, then sort the vector, then copy back to a list. Any reason for doing that? Yes. It is more efficient. It is more efficient because vector is local, so you get cache locality. This is the benchmark. You can later see the code itself. And of course, we take into account the copying inside the code. I mean, we count for the two copies from the list to the vector, sorting the vector, copying back, and it is still much more efficient. You should remember that benchmarks are dependent on the exact machine, the exact data set, which means that don't rely on benchmarks that you just saw in talk. Go do your benchmarks on your own data before getting a decision on, okay, I'm going to do that in my code. I'm getting back to my work, and this is the first thing that I would do. No, benchmark, check. A question? So the question is why or whether the implementation could do the same. It might be, but it seems that it doesn't. I mean, I compiled it with, I think it is with libstd C++, and I do see the difference, which means if it would do the same, it would get the same performance. I guess that this approach is good for some data, and it is not good for other data, and we can think of when it is better and when it is not. Like, for example, it might be that if the elements are big, or the comparison of the elements require getting out of the element with a pointer that points outside, maybe the cache locality would not help us in the sorting. We can think of cases where might be that it would not help us sorting it as a vector or not. So anyhow, yeah, the implementer could implement it as copying to a vector. Okay, it seems that it didn't. The question is about the data types. So yes, it is chars. If I remember correctly, it is a large string that I copy outside of the benchmark itself to the container. So it is at the end characters. It's a vector or a list of characters in this case. But again, it depends. It depends on the data. It depends on other factors. Insert to front. What is the best way to insert k items as a bulk into the front of a vector? Or maybe would it be better to use a list? Well, in fact, a vector doesn't have a push front function, but you can push to the front of a vector by calling insert. You can insert to the begin. So if I insert to the begin, which means that I actually push front, suppose that I have to push front a few items. Would it be better to do that on a list? Seems so, because if I push it to the vector, I have to push the vector ahead. Is there any better way to push several items into the beginning of the vector? So it is a bit tricky, and the trick might be reverse the vector, then push back in opposite order, then reverse back. Oh, sounds insane, and yet this idea comes from a talk by Vladimir Vishnevsky, sorry for saying the name, from, again, C++C. Again, the link points to the abstract. And I would just show you the benchmark. Push front with a trick. And again, it depends on the data. But with the proper data, you would get better performance with this trick. Not always, which means, again, you have to think, what do you want to achieve? By the way, the push front on list is equally perform as the push front to the vector, because building the container was part of the benchmark. So building the list and building the vector of the list is a bit more costly. Anyhow, these were the results. I think that you all heard that the same as stood move doesn't move, which is not always the case. There is a stood move that does move, right? But there is another one that doesn't move. The stood move for our values, for a conversion to our value, doesn't really move. It's a utility. The stood move in algorithm does move. And stood remove doesn't remove. I think that might be that you heard about that. This is a question, by the way, in Stack Overflow. Somebody uses stood remove and says, I used stood remove and I didn't get the expected result. Well, it says so in the spec. Stood remove overrides the removed elements with consecutive elements that should be kept. It then returns an iterator to the new end, which is still inside your container. Maybe if you actually want to erase, which most usually you would want, you should call erase after you call remove. So it is known as the erase remove idiom. And the idea is that you first copy the elements that you want on top, override those that you want to remove, and then you just get rid of the rest of your container. It looks like that. Suppose that the original container was these numbers. I wanted to remove all the 9s. You can see that the 9s are removed. Even though I do have 1 9, the third from the end. Why the third from the end is still there? Because there was no other element that could override it. I mean, there were 3 9s at the beginning. I mean, at the original container. The first 2 were overridden with other elements. And the last one, which is here, no one came to override it, and I just finished. I mean, there isn't any one, and the return value is an iterator pointing to this 9 saying, well, this is the new end, or this should be the new end. It is still not the new end. The size of the container is still the same. And then you need to call erase if you actually want to erase them. It might be, that, by the way, that you do not want to call erase because maybe you just want to iterate of them, and the whole container is going to die anyhow in a moment. So it is kept to you, to your decision, whether you actually want to erase or you say, oh, this is the new end, I would keep the container as is and use the new end. Might be. Anyhow, if you do want to erase, then you erase all these 3, all the rest, using the iterator that you got. In C++20, there is a new function called erase that actually does the same. It gets the container and it does the 2 operations. Okay, so eventually it should behave the same. And also erase if, which again do the remove if and erase on the result, the same as we did here, quite manually. Erasing by index. Let me ask you a question. What is the complexity of erasing k elements at given indices? So we have indices for deletion. They are sorted in descending order, just in order for us that it would be more efficient or more easy. And we want to remove them from a list or from a vector. So let's think about that. We have k elements. We need to remove all k elements. The elements are given as indices. Can we do that in ON on a list? Yeah, we can iterate over the list and we can just erase those that are marked, right? What about a vector? Well, the problem with a vector is that once we erase an index, then again, the vector needs to shrink, need to move. And if we do that on all k elements, it would be k of n. Might be that k is big. I don't know, k is a constant. We can ignore that. But anyhow, there is something costly. Can we do something a bit better with vector? So this is erasing by index from a list. We get the begin. We get the position of the first one to erase. We advance to the position. And again, this is from the end. Why? We got the indices from the end. And inside, we just run over all indices. And we we advance the iterator back. It is going back here. The first one is 0. The first one is index minus pause. And index, the first index is the same pause that we got here. So the first one is, okay, just take the iterator and go there, and then erase that. And in the loop, we just go back each time and erase one. Okay, that's the idea for a list. If it is a vector, we can just call erase on all indices. Now, since we are doing it from the back, from the end, I mean, they are in descending order, so no problem. The indices are not changed for those that are before. But this is not so efficient. What is a better way to achieve the same? Well, we had the idea of remove and remove if, but remove and remove if works on you tell them what is you are looking for, what is your lambda or your predicate. I don't want a predicate. I just want to give you an index. So we can actually call studMove in order to move bulks and then shrink at the end, which is quite the same as the erase idea. Now, usually, when I write code, I just, at the end, do a benchmark, show you the benchmark. But here, I wanted also to do some asserts. So the code here asserts that, yeah, it actually works. But when we go to the benchmark, we see that the erase with moving, I mean, this algorithm would be better. Because you shrink to the proper size only at the end and not during the entire loop. As homework, there is homework. I didn't tell you at the beginning, sorry. As homework, I would let you implement a more efficient erase by indices from vector by running on the indices in ascending order. Can you do that in ascending order? Well, if we actually calculate what would be the next index after we erase, yeah, we can do that. Why can it be more efficient? Because we would move smaller bulks. The bulks that we would move would be only to the next iterator. So to the next one that we need to erase. This would be for homework. I would just show you the benchmark maybe. It's very similar. It's very similar. But it is a bit more efficient. In many cases, when there is such a small difference, it might be just pure luck. But it seems that there is some difference here. I mean, it is 10% more efficient. Don't look at the code. It's your homework. Okay, so it was running from the beginning. What is the complexity of calling find or insert on a map, unordered map? Unordered map is implemented as hash table, right? So we have buckets. In the buckets, we have linked lists, something like that. So we all remember that it's constant. It should be O1 because we just find the bucket and the list should be quite small. I mean, the list should not be proportional to the actual data set. If it grows, there is a rehash and then it shrinks. But the spec actually says that it is O1 on average, but ON on the worst case. And I'm trying to understand together with you what is the reason that it is ON, it is linear on the data set, even though a hash table is designed to give us O1, probably for find. So what is the reason? Yeah, it might be a bad hash function, yeah, but I would tell you that even if you have a very good hash function, in some cases, which might be most of the cases, the worst case might be ON, linear, even if you have a good hash function. So let's take a case that you have to map keys, and the keys are strings, okay? How many strings are there out there? A lot. More than size T? Yeah, I would say more than size T, because the max string is size T, right? The max size of a string is size T, let's assume. So what is the number of strings out there? 256 to the power of size T, something like that. Maybe more if you are on wide char. Anyhow, it is much bigger than size T. Now, eventually, you take your population. It is not that you are going to map all the strings out there. You are going to map some strings, but it might be that the mapping from a string to a size T value requires a function, yeah, it requires a function, that would, in some cases, maybe deliberate. Maybe it's, you know, an attack by someone that would take strings and would give you back the same hash code. I mean, you can find those strings that give you the same hash code. It might be not the strings that you are going to use, but yeah, the population is much bigger than the size T of the hash code. So the spec needs to say that you cannot implement a find which worst case is O1. The worst case might be not because of a bad hash function. Yeah, it might be a bad hash function, but it might be a very good hash function, and yet you got a pathological case where all the data just fell, or maybe it was deliberate, on the same hash value. By the way, to avoid such attacks, there are other algorithms to create a hash table with some kind of another hash function which would be harder to attack. Beware of costly hash functions. In some cases, we believe or we think that the hash function is called only when you insert the value, the key, to the hash table, to the unordered map, and this is not necessarily the case. There is code here and a question in Stack Overflow that shows that in some cases there is some access calls, more than you would presume, to the hash function. And if your hash function is costly, okay, you should consider that. What's wrong with this code? If you're looking for dangling references, temporary that dies, I think that the temporary here is kept by the loop. So we have a temporary vector, but it is being kept by the loop. All the char stars are still alive on the data segment. So we do have a valid vector of pairs, and we loop over them. It's C++17 structure binding, so we bind them by value to A and B. It's okay that we bind them by value because they are const char star. So eventually, A and B are const char star that we get in the loop. And then we call numbers, which is a unordered map or map here, and we just want to insert a new value into the map. So what can we do better? The code works. You actually populate the map with 1 pointing to uno, 2 pointing to duo, etc. Where the problem is that when you call to square brackets means insert or override. So eventually what happens there is that a new string is being created on the left side and then being overridden, then being assigned to. And the new string that was created was an actual string. There was a very small allocation there, but there was an allocation that is being deleted and being overridden with the actual string that I need. So in C++17, they added a function called insert or assign. Now, in this case, insert or assign would do better. I do want to assign if the actual value is there already. I mean, if you only want to insert, just call insert. That's the easiest way in this case. But suppose that I do want to assign if the key is already there. Yeah, I want to override the value for the same key. Yes, but there is a better function in C++17, insert or assign. And there is a benchmark for the same case. So it's not the exact same case. In order to show such a nice result, I actually created a key that in its constructor allocates a big string. I mean, I did something that would be a bit costly in the constructor of the key in order to have something like that. Otherwise, it would be very similar because the constructor of empty string is not so costly, but it is. It's not free. So yeah, if you want to assign, use insert or assign. If you just want to insert, use insert. And we have a question from David.
So the short string optimization probably makes so it doesn't make a difference.
Yeah, but it's either that you have a big string inside, or in other case, it might be, if you have a short string optimization, small string optimization, then it means that when a empty string is being created, there is no allocation. And then when it's being destructed, nothing to delete. So I created here some kind of another key which does have something in the constructor. So it's not the exact same example that you see here. The benchmark is on some kind of a case where you do pay for the allocation or for the creation of the object that you are going to override, to assign to. And most usually you know that it is a bad practice to create something, go to the constructor, and then assign to it. And this is, by the way, the reason that we use the constructor initialization list. Usually we prefer using the constructor initialization list and not to assign inside the constructor, because when we assign in the constructor, we create the object, and then we just say, oh, drop what you just put when you went through the constructor, we have something else. It's nice that everything that I say is here. I'm teaching, I just said that, and in my lectures, in some cases, students ask, what was the last sentence that you just said? And here, it's quite easy. I can go back and say, I just said that in my lectures, in some cases, a student asked what was the last sentence that you said, and it is quite easy. It's nice. C++17, you may want to use insert or assign. And again, in some cases, like small string optimization, the difference would disappear. But in some cases, it would not. And again, it depends on your key. C++17 added other additions, like, for example, we have in place on map before C++17. I mean, we could call insert in order to insert a pair into a map, but we could have call in place, and here in place would create the person here, the person named Coco, inside the callee, inside the map. So we call the constructor on the other side. So we save the need for a copy or for a move, okay? But what is costly here is that it might be that when we call in place, the key is already in the map. So we create the guy on the other side, on the map, and then the key is being checked, and oh, sorry, you are there. And we get back a result saying we didn't insert because the key is already there, with the iterator pointing at the one that was on the map. So they added in C++17 try in place, and try in place would not create the actual object if the key is in the map, which is smarter. Now, in some cases, it might be that in place would be better if you know that the key is not there. Why? Because then the in place would create the pair and just put the pair. It would move both the key and the value into the pair, where here, I think that the key
the pair is created at a certain point where you didn't move the key to it. I think that there is some kind of, if the key is not in the map, and you know for sure that it is not in the map, then emplace would be better for some reason. We need to think about that. Anyhow, if you do not know, then try emplace would be better. So this was C+17. This is again a benchmark, and again, for some, you already, I think, realized that for some cases, in order to have the difference, we have to cook the key in a bit, or the value in this case. We have to create a case where, oh, it is quite costly to create the value. Otherwise, it would be very similar. But there are those cases, and again, it depends on your actual code. Don't go and you are in C+17, don't go and change all calls from emplace to try emplace just because you heard about that, unless you see that it is indeed costly. A new type in C+17, usually it might be that you go to CPP reference and you see, let's say, a function that returns something, and then there is a comment saying you should not know what is the type that will return. In some cases, there is a type, and the type is templated over some kind of a template, and the template is some kind of a comment inside CPP reference saying, oh, you should not know what is the template argument. And in this case, it's quite strange. You have a type, and you actually don't know the name of the type. So there is a type, a new type, C+17, called, oh, sorry, I don't have the name. So let's have a nickname. The nickname is node handle. So we have a node handle, which is only a nickname for a class which we do not know the name. How can we use a class for which the name is not disclosed? Well, we use for that auto. Auto is our friend. So it was added in order to allow extracting nodes from map, unordered map, multi-map, etc., to merge and to insert node into a map. So let's take an example. Suppose that we have a map, 0 pointing to 1, 2 to 2, and 3 to 3. Oh, sorry, 0 should not point to 1, it should be 1 here. Oh, so let's fix it. Let's extract the node with the key 0 and get back a node. What is the type of the node? I don't know. I guess the implementer know. They should know. The spec didn't say what is the name of the type, so let's use auto. So we got here a node handle, okay? And it would be possible to change the key. So usually the key is constant, but we have a function called key that allows you to change the key on the node handle. So when I called extract, the node was removed from the map. It's not there, okay? We just removed it. And then I changed the key, and then I inserted back the exact node. Now, we could have done that before by erasing and inserting the actual node that we wanted, but this is better. How can we tell? Well, we can benchmark. And again, it is a bit better. So you want to extract something? Use the node. There is a node. Somebody paid for creating the node. Don't create the node again. Okay, let's do that. This is C++17. The type is node handle, and we used it with extract and insert node. By the way, there is something quite similar on list with splice that was, I think, since C++11. But with map, it was added in C++17. For list, it's not for extracting a single node. It is for merging nodes. There is something on splicing a list. So this was what we did with node handle. Other additions. There is a possibility to try and place with a hint. If you are on a map, it is more relevant for a map than for unordered map. But if you are on a map and you know the position where you want to add a certain key, because you can imagine the structure of the map. It's a binary tree, and you just created that. So you can give a hint to the emplace and call try emplace and give a hint, okay? Don't do that. Or prefer to make sure that it actually helps, because it might be more costly than beneficial. If you give a wrong hint, it would go to the correct place. It checks your hint. but then it would traverse over the map on locations where it shouldn't. And then eventually, oh, this is the place, you just told me the wrong direction, and you pay for that. If you give the right hint, it may help, but it is very small. So most cases might be more harmful than beneficial. There is a benchmark here showing that even if you give the right hint, it is not so beneficial. If you give the wrong hint, it's bad. Views. Well, views were added in C+17 with string view and then in ranges in C+20. The idea of views is quite useful. I need to speak with some object. I don't need a copy, and I even don't want to move it, either because I just want you to continue holding that. Maybe it's an L value, but I just need to iterate over that, to read something, maybe to change something. I don't want a copy. I can even take a char star or a string and view both the same way. So I would not dive into how to use views, but you should view how to use views. Take a look for a talk. Views would make your code more efficient, where in the past maybe you got const string ref and then maybe copied, or maybe you got a char star being sent to a const string ref, and the char star created a new string. You don't need a new string, you just want to iterate over characters. So getting a string view would be more efficient. So you should take a look at views. Other data structures. So we have boost flat map, and in C+23 we should get flat map into the language. And flat map is quite wise. It has a vector of keys. It might be other data structure, but eventually it would. The default is a vector of keys and vector of values. And lookup is logarithmic. It's a binary search. The keys are sorted. And the idea is that you preserve data locality. And data locality is quite important. So we still don't have it in the language, but we would have in many cases where you actually iterate over keys or iterate over values. In a way, it resembles the idea of structure of arrays instead of array of structures. If you know the comparison, if you want data locality and you loop over the same field on many objects, it might be more efficient to have all fields in the same vector. So there is a notion of, do you prefer vector of structures or struct of vectors? And here, I prefer, if I want to traverse over the keys or over the values, to have them in a contiguous data structure. Two calls to std algorithm. What is the cost of two calls to looping twice on a data set compared to having one loop doing the same two operations? I mean, there is one loop doing two operations, or two loops, each one doing a single operation. Which is more, where is the complexity higher, or they share the same complexity? One loop, two operations in the loop, or two loops, each one doing a single operation. It's not a tricky question. Well, both cases do n times, do some operation on all n items, and do it twice. But 2n, if the time is 2n, then the big O is n, because we ignore the constant. So does it mean that they are actually the same? Well, you know that the complexity-wise, even if two things are the same, it doesn't mean then practically that they would cost the same, that they would have the same performance. What is the advantage of a single loop? Cache locality. We have the data. We work on the same data instead of running on that twice. So you can see again, I would not go through these benchmarks, but we calculate here two things. One's with a list, the other example on a vector and data locality, cache locality wins, which means that in some cases, we have algorithm and we want to use two algorithms, but we need two algorithms, which is quite problematic because eventually we would prefer one loop because then we would have cache locality. And then comes to our help, ranges. So ranges would help us in a way because if you use ranges, there is an idea of some laziness at the behind. I would not go to this code example, but you should, for example, go to Dvir Yitzhaki talk on ranges. This one is on the web, or any other talk about ranges. You can have a few operations, one after the other, and then only the last one would run the loop, which is what we wanted, but still we're using algorithms, okay? So this is quite wise, and for that you need C++20 or the ranges TS. Parallel algorithms, C++17 added parallel algorithms. I would just say that if you want to use parallel algorithms, do a benchmark because in some cases it would just hurt performance, though in many cases it may help. You can use a parallel algorithm for, this was about the parallel algorithm and the execution policy, and again the talk in C++C by Vladimir Vishnevsky, and a very good talk that covered much more than I cover here with many examples. And other resources on that. There is a difference between execution par, which is for parallel, and execution unsec, which is for a single thread asking for vectorization. If you ask for parallelism for execution par, and of course you need the library to support that, then it means that you are going to use, or you're asking to use multiple threads utilizing a few CPU cores. It might be that you need these cores for other processes. It might be that you need these cores for other threads running in your application. So it might be that it is good for your algorithm, but your process needs these CPUs for other things. That then again, you have to, it might be that the benchmark shows, oh, it's good. Yeah, but I'm exhausting my CPU for a single algorithm. In the same time, there are other threads or other processes on the same machine. So you have to consider that as well. Thread safety, always check thread safety. C+11, before C+11, the spec didn't speak about concurrency at all. There wasn't any notion of concurrency before that. In C+11, concurrency came into the game. And then there is something about thread safety that was said, which yeah, we can assume, but you can never assume the spec needs to say so. If you call two const functions on the same container, even if there are different const functions, functions that are marked as const, then they are thread safe. The two calls are thread safe, if they are both const. Now, somebody can say, yeah, for sure, they are const. They do not change anything. Yeah, but they can change a mutable data member, or they can change a static member, so they shouldn't. I mean, or if they do, they need to use atomic or some kind of a lock. So eventually the spec requires the containers to comply with two const functions being called from two different threads are thread safe, and all the rest is for you. So you should be able to make sure that your code is thread safe. Iterator invalidation is also something important. And again, these are some links about iterator invalidation. One of the known bugs is getting an iterator to a vector and then calling pushback and then using the iterator. The iterator might be invalidated because the pushback just moved our vector. References and iterators to vector after pushback are not, might be invalidated. If you're going to implement your own iterator in C++17, they deprecated the std_iterator base class. The std_iterator base class gave us some ability to a bit more easily implement an iterator. What is the reason that you think that they decided to deprecate std_iterator? In a way, it gave the notion that it is an interface for iterators. I mean, oh, I got an iterator, so I can hold it as a std iterator. No, a std iterator is just a utility class that was used in order, if you want, you are not obliged to implement your own iterator. But you are not obliged to use that. And if people would be confused and think that, oh, all iterators are being derived from std iterator, it's a wrong notion. So I think this is the reason they decided to drop that. And then the question is, okay, so if I want to implement iterator, it requires some boilerplate. Yeah, you can take it from Boost Iterator, or you can implement it yourself. Here is a link. Another question that we may ask is, how is reverse iterator being implemented? So this is iterator. The begin points to the first one, the end to the end. Would reverse iterator point, the begin would point to the actual last one, the legitimate one, and the end would point to one before the begin? What do you say? Is it a good implementation? And the answer is no, it is not, because you cannot point to one before the begin. One after the end is an address that you can point to. I mean, any position in memory, you can point to one past. The specification says so, but you cannot assume that you can point to one before. So there is a very simple implementation saying that no, the end would be the first one. The begin would be what was the end. But when you call the indirect, when you want to get the content, then I would bring you the content from one before. So don't call star on the end, because I would try to bring it from here. Yeah, you should not. But you can call star on begin, because I would bring the content from this one without moving the begin. Only when you say plus plus, I would move the begin to here, and then it actually thinks that it is here, but it would bring the content from this one. This is how reverse iterator is being implemented. And again, these are small details that the implementer needs to follow, otherwise the code is ill-formed. The code has undefined behavior if you point to somewhere in the memory that you should not point to. Summary. Picking the right container. The spec is, in some cases, rhymes. So the green box is from the spec. When choosing a container, remember vector is best. Leave a comment to explain if you choose from the rest. This is actual phrase, actual sentence from the specification. So try, I mean, go with a vector, unless you have a benchmark showing that, oh, here list would be better. Unordered map. Well, in some cases you need associative container, so go with associative container. Unordered map should be your choice, but you have to think about the hash function. The spec itself says that hash function should have good distribution. So you have to think about your distribution, not to have a bad formed hash function. And yet, it might be that your good hash function can get the worst case of a linear find call. Using std algorithm, don't invent the wheel. If you implement your own sort, it might be that you would implement bubble sort. I do see things like that. Yeah, I decided to implement my sort. Yeah, but it's O(n) square. It is not what you wanted. Think before. Implications of bad algorithms and improper use of data structures are potentially much bigger than any micro performance improvement. And in some cases, you would not see it in profiling. I mean, you see in profiling that something is costly, and it should be costly. My main algorithm is there. But if you would think, to begin with, about the algorithm, maybe you could do something better there. Switching to a better algorithm can decrease runtime dramatically. Be aware of invalidation rules and thread safety always. Don't focus only on big O. We discussed cache locality. And in real life, constant are important. 2n is better than 4n, even though usually we just ignore the constant. Yeah, but you know, twice the time is not so good. Ignore the constant. So when we ignore the constant, it's something that, again, as said before, we should think about that. time of C multiple n is big O of n, but let's take a look at this algorithm. In this algorithm, we run on all the data is the vector, and inside we run 100 times on something. So eventually, the complexity is 100n, but 100n is big O of n, right? But we still have the 100 there. And if we could have another algorithm which would be n log n, would you prefer n log n or this one? I mean, this one is O(n). Which is better? I have another one which is n log n, or I have this one which is 100n. 100n is O(n). Well, eventually n log n, what is the biggest size of log n? Well, it depends on n. What is the biggest size of n, for example, on a vector? Size t. What is log n on size t? 64. 64 is less than 100. Again, it depends on the architecture, etc. But most probably, the log n is smaller than your 100. So ignoring the constant in some cases is a bad practice. I mean, yeah, you should think about the big O, but then think also about the constant. You may reduce latency with trade-offs like prior setup. We discussed that. Copy to a vector, sort the vector. It's a prior setup, you pay for that, yes, but then the operation is more efficient. Space versus time, using caching, indexing, etc. So you pay for space, but you have better performance. When you do benchmark, take a look not only for the small amounts, but also for the big amounts, and you have to think, what is my scale? Because in some cases, like, and again, this is from C+ on C, and again, Vladimir, a very good talk. And here, vector and list are being compared, and list is better at the beginning. No, sorry, vector is better at the beginning. So if your benchmark is only for this size, you may assume that vector is better. But eventually, if your size is much bigger, then look at the bigger picture. Look at the scale. So you have to think about your scale. And it is not pre-optimization. Thinking about the right container and algorithm complexity is, in many cases, people say, don't pre-optimize. Because pre-optimization is paying for something that you may not need later. Well, writing inefficient code is not something that we want. So you should think about that. You should not create monsters for something that you do not need. But having the proper container or the proper algorithm is, of course, important. And that's my talk. Thank you. I think that I have time for one question or maybe two. But I can also take questions offline if you feel that you prefer that way. Yeah, a question, please.
If your data is highly variable, have you ever tried changing the container that you're using at runtime?
So the question is it something that you should consider changing the container in runtime based on the data that you're using? Well, you can do that like some kind of a strategy pattern. So you have some kind of a strategy for this amount of data, and then when the data size is enlarged, increases, then you move to another container. Yeah, it can be done. You can also use template specialization for maybe the size is known at compile time in some cases, and then you use the same container, but the container which is picked at the behind is either a sparse matrix or a simple vector. So yeah, you can achieve things like that. Any other question? So thank you very much for being awake after lunch, and many of you were not only awake but participated and answered. So thank you very much.